Hi, everybody, and welcome to session number 2 of this year's ANITA Not So Summery School. At least in Melbourne at the moment, it's definitely not particularly summery, but at least we're about to be out of lockdown, so that's good news. And even better news is that today we get to hear from our fantastic ADEX teachers, Paul Hancock and Rebecca, who are going to be teaching us about how to test that our code is sufficiently optimized and look for bottlenecks and all sorts of other wonderful things that are going to allow us to write both better and more resource efficient code. So without further ado, I'm going to turn you over to Paul and Rebecca.
Thank you, Ilya. So welcome to the ANITA school. We have planned for you today 2 sessions. So there'll be 2 90-minute sessions. We'll have a bit of a break in between for people to get coffees and whatever. So hopefully people have had an opportunity to look on some of the emails and check out the various resources that are needed. But to get everybody started, I'm just going to link here in the chat a link to the GitHub repository, which has most of what you need to get started. And in particular, one of the things that are linked at the website are the link to the slides, which I will be presenting today, and also to the workshop that we're going to be doing this afternoon. So let me share my screen. Just press the button. Okay. Okie dokie. All right, so hopefully if I present, everybody should be able to see that. No, it's jumping around. Okay. All right, so so this is the Green Computing School. This is session 1, and Rebecca and myself will be hosting this. And Rebecca and I are both from ADEX. So before I'd like to acknowledge the custodians of the land that we reside on. And in my case, this is the Whadjuk people of the Noongar Nation. We'd like to pay our respect to their elders past, present, and emerging, and acknowledge and respect their continuing culture and contribution that they make to the life of this city and of this region. So other things that you will need to effectively participate are firstly these slides. So the ones that I'm showing at the moment, you can access via this tiny URL or linked directly from the Git repo, which I linked in the chat. There is also a collaborative Google document, which I encourage everybody to open up. There is this information and some other information in that Google Doc there. And also there is the Git repo, which I've already linked in the chat. So I'll let people get a hold of some of those. Obviously, if you're just going to watch my screen, you don't have to follow the slides. So just a bit of sort of housekeeping before we begin. So obviously, it's great if everybody can mute themselves, and I see that pretty much everyone has done that, so thank you very much. If you have a camera that is even slightly reliable, if you can turn it on, that's great. It means we can see all of your faces, and we can see people when they have questions even before they raise their hand. Also, if you do have questions, you can either press the raise hand button, or you can just type your question into the chat window. And we will either one of us will either answer your chat messages in the chat window, or I will maybe interrupt myself and answer the question to everybody, depending on how we how relevant we think it is. But also be respectful of all participants. So choose your words purposefully and give people room to speak, especially if you're in a breakout room, and support each other. So we're going to follow the Carpentries Code of Conduct, which I've linked here, which at a high level, it says just, be nice to people. But in particular, what we really would like to do is to foster communities and foster working communities where people can support each other. And so I'd encourage you all to have a look through the other participants who are here today, and to consider these people sort of your peers, your classmates, and people that either today or in the future you might chat to get advice from and to get help from. And that includes Rebecca and myself. So let's do some introductions. So we are ADAX. Rebecca and I are representing the Astronomy Data and Computing Services. ADAX aims to coordinate and maximize computing and storage resources available to astronomers through a mixture of direct development infrastructure, facilitating access to existing resources and support. So what that means in, I guess, more plain text is that we want to increase the capacity of the Australian Astronomical Society. We would like the members to be able to draw upon a wider range of resources, and importantly have the skills to be able to make best use of those resources. So many of those resources that we focus on are HPC, but cloud and other computing infrastructure is also a viable target for our training and support. And of course, some of the things that we do are to provide direct training, such as we're doing today. So just a little bit of a background. Both Rebecca and myself have PhDs in astronomy. We are both now data scientists at the Curtin Institute for Computation. So this is a group within Curtin University. And we train developers, we are training, there should be a comma there, training developers and providers for ADAX. So you know who we are now, and we'd like to know who you are. So if you can go to the Google Doc and introduce yourself and answer the icebreaker question. And as I already said, if you can turn on your camera, give everybody a wave to say, hello, this is me, that would be great. So, oops. What I meant to do was click that Google Doc. So this is the Google Doc that I was referring to. As you can see, some of the information is just repeat of what I've already said. So if I can get people to fill out here, the attendees, just like Ollie has already done, thank you very much. And then there's an icebreaker question here, which is meant to give us some insight into who you are, but also maybe spur some conversations, some offline conversations maybe. Don't worry about this next section down here at the moment. We're going to get to that a bit later on. So I'll give some people an opportunity to fill this in. I guess I should probably fill it in too. I should also have thought about these questions that I was asking myself. Oops. Looks like people are getting a little bit excited and over-typing each other. It's all fine. Okay, so we've got Queensland, Melbourne, Perth, Melbourne. Lots of Melbourne people. Melbourne. Another Perth person. Excellent. Melbourne. Let's see. Oh, wow. Is Top Gear a children's show? I guess so long as you're watching the TV show whilst you were a child, it counts. Oh, Around the Twist. I remember that. That was great. Okay, all right. We've got some interesting answers here, some of which I've never heard of before. Alrighty, I will let people continue this and continue the conversation. Let's return to our slides. Okay, so in the two sessions that we have today, the first session is going to be primarily me talking and you asking questions. The second session today is going to be primarily everybody doing work using some of the software that we've asked to be installed. So what I'd like to do is just quickly go over some of the software setup now so that people can identify any problems that they might have before the afternoon session. So for today, the requirements that we have are hopefully pretty easy for you to satisfy. So using whatever package manager you enjoy the most, either Miniconda or Anaconda, you can use the environment.yml file, or there's also a requirements.txt file if you have a sort of more generic Python environment manager that you're using. But at the end of the day, so long as you have Python 3.6 or above, and you have the packages that are described in the environment.yml or requirements.txt file, then we'll be good to go for this afternoon. That's the only requirements that you should need. And I think Rebecca has already identified an issue with the YML file, which is 100% my fault. And in fact, I will just now quickly fix things on the Git page. Okay, so that's for this week. For next week, you will need some kind of bash shell. If you're running a Linux-based machine, then bash is fine. If you're running a Mac, then your term will be fine as well. If you're running a Windows machine, as I am here at home, then you'll need to use something like git bash to be able to engage with a lot of the content for next week. So if you go to the GitHub page, which I linked previously, then you should be able to clone the repository. So on my machine, this is how I would do it: git clone this whole big thing here. That will give you a new directory, which is just ANITA 2021 Green Computing School. So if you cd into that, and if you're using Conda, then this is how you would do it: conda n create, and then activate that virtual environment. If you're using pip or something else to manage your packages, then you can just do pip install -r and then whatever the name of the file is. What did I call it? Yeah, requirements.txt. So this might take a little bit of time to download, depending on whether you've got Anaconda or Miniconda. The requirements that we've set are pretty minimal, but depending on your system, it might take a bit of time. So what my recommendation is that you start doing this now, and if you hit enormous problems, kind of put a little pin in that and either ask for some help in the chat, or maybe in the break, we can also provide some more generic or focused help depending on what's needed for people to get things working. Okay. All right. So that's about all I'm going to say about that. I'm going to let you all sort of run off and do that in parallel. Hopefully a low resource usage part of your brain can take care of that whilst you're listening intently to the rest of the talk. So after the talk that we had, or the panel discussion that we had last week, actually all about green computing, we thought it would be good to have a bit of a practical, here's how you can do things, here are some takeaway lessons. And I found that the discussion and talk last week was extremely interesting. It was a little bit of a roller coaster in that it kind of felt like no matter what you do, you're always going to be using resources on the computers. You can't optimize your way to zero. It's a bit of a sad state. But at the end of the day, the solution was, if your ultimate goal is to generate less carbon, then just switch all of your supercomputers over to renewables. So from that perspective, I think, in terms of saving the planet, combating climate change, that's the ultimate solution that we want, and no level of optimization or amazing performance on our systems is going to get around that. However, I think there is a more general trend, or a general mindset that people should try and take, and that is to, regardless of where your resources come from, you should use as little as possible. You should only use the resources that you need, and you should leave the remaining resources either unspent or available for others. And that's where optimization comes in. So I'm going to give what I think is a fairly high level view of optimization. And then as we go through our first session today, we're going to get deeper and deeper and kind of more specific about a particular language, which is going to be Python, and a particular kind of optimization, which is CPU usage. But we're going to have a bunch of call outs to some other cases as well. And then next week, we're going to open it up again and start thinking about optimizing at the most highest level. Okay. So with that preamble in mind, let's begin. I do have a chat window. Okay, all right. I'll put that over. Let's put it here. Okay, so let's say from the very start, optimization is essentially just making things better. It is a very general term because better can refer to a number of different things. So a better performing code or a better performing program could use less CPU, could focus on less RAM usage. You could be more concerned with the I/O, reads and writes. You could only care about your time to completion, regardless of resource usage. Or you could be concerned about the lower energy use or CO2 generation. Okay, all of these things, these are all valid targets for optimization. These are all different ways that your programs can be better. And I'm not going to tell you which of those is more important because that's up to you. So it depends on the task that you're doing, and it also depends on the environment in which you're running as to which of these things become more important. And you have to make choices because it's impossible for you to min-max everything at once. You can't minimize CPU and RAM usage at the same time. Typically in many algorithms, there'll be a trade-off between how much RAM you're using and how much CPU you're using. Similarly for I/O, if you engage in caching a lot of results, that can help to reduce your CPU usage. But of course, the cached data needs to go somewhere. So that's either going to sit in RAM or it's going to sit on a spinning disk somewhere. So you're again trading CPU for RAM. And if you're looking for faster time to completion, then sometimes you just put as much CPU, RAM, and IO as you possibly can in your system so that your program takes less time to run, which is a less efficient use of resources, but you're hitting that target time to completion. Something that came up at the discussion panel last week was that the lower energy use is something that people are more aware of and would like to be able to at least measure or understand how much energy or CO2 equivalent they're generating as a result of their computing. But on every system that I have ever used, that is not something that gets reported. Typically, all of your allocations for supercomputers will be in CPU time. So something like a combination of cores times nodes times hours is how you're allocated resources. And then all of the other things kind of just flow on from that. So that's a little bit difficult. And I guess also the energy use depends even more specifically on the system that you're using. But hopefully into the future, people such as Pawsey will start to allow people to report an approximate energy use for their project for a semester. And potentially even calculate a CO2 equivalent, and maybe people can start to try and minimize that. Okie dokie. Let's see. Yes, impossible to min-max everything at once. That's just the way that the universe works, unfortunately. So something that I would like to suggest, and I would say strongly suggest, is that we take on a bit of a workflow mindset. So to me, a workflow mindset is where you're thinking not about your specific piece of code or a function or the bit of software that you're working on, but you take a larger, a wider view, and you view the entire workflow. So in this workflow mindset, you first identify what your goals are, then you identify what inputs you have, and then the tools that you have available. And quite simply, a workflow maps the inputs onto the goals using tools. Now, a workflow, here we go. The idea here is that you're trying to optimize your total workflow. So Armdale's law in computing says that the system speed up is limited by the slowest component. And my rule of thumb is that you are the slowest component. The people are the slowest component in the workflow. And so in order to optimize your total workflow, what you should firstly focus on is reducing your active interaction time. So if you have some blindingly fast scripts that run on a supercomputer somewhere, that's fantastic. But if you have to manually load and move the data around, if you have to spend an hour or so writing configuration files in order for this script to run, which only takes 5 minutes, then your workflow in terms of identifying a piece of work that needs to be done and then having it completed is really, really slow. And it's mostly you messing about with fairly mindless tasks. So you should really focus on reducing your active interaction time. And then you should focus on reducing your total wait time, which is the time that you're sitting there doing nothing, waiting for your resources to do all of the computing for you. And then you should think about the CPU time. So number 2 is more about the wall time, and number 3 is about the actual CPU time. So hopefully everybody has seen this XKCD before. It's about, ultimately, it's about premature optimization. So depending on how much time you're saving and how often you do the task, this is essentially a matrix of how much time has been saved. So something like this is a good starting point for you to understand that if you if you identify a method that's going to give you 30 seconds reduction on your compute time, and this is a task that you run 5 times a day, then over 1 year, you're going to save 3 days. Now, if this means that if this is something that you can implement within 20 minutes, then that's great, because you've saved 3 days worth of effort over the year, and it's only taking you 20 minutes to implement. So this sort of thought process of how much time are you actually going to save by doing this optimization is something that people need to consider, because premature optimization can be the root of all evil. I see people who like to have extremely performant code, and they spend a lot of time writing that performant code. And if you're doing that out of a hobby, then that's totally fine. Go for it. I'm not going to stop you doing that. But if you're doing it because you believe it's going to give you some net benefit in your research output, or it's going to make you graduate faster or something like that, then you actually need to step back and think about, well, how much time am I spending optimizing versus how much time am I going to save? And I think something that becomes more and more true as you progress through the sort of fairly standard academic career path of going from a postgrad to a postdoc, a ECR, and then up to faculty, if that's how far you want to go, then what ends up happening is that, during your honors project, you're doing exactly one project. And during your PhD project, you'll have a couple of different projects that are all together making up your thesis work. And as you progress, you're working on more and more projects. So in fact, a lot of the time, you don't really care about how long your piece of code is taking to run, because you have plenty of other pieces of work that you can actually be doing in the meantime. And I would suggest that this is at least part of the reason why you see many senior academics just not caring that they're using a very inefficient computational method, because to them, it's not the bottleneck, it's not slowing them down. Potentially also, they haven't come to these ADAX training workshops and they don't know how to do the optimization. Anyway, another thing that I want to say is that not just with optimization, but with anything, is please verify that you have a problem before you spend resources fixing a problem. So if your piece of code takes an hour to run and you think, oh, that's not good, I could do it in 20 minutes, just do back of the envelope calculation, have a look at what other work you're doing. And if that piece of code is not the bottleneck, then making it run in a shorter time isn't going to help you. And I guess another way to say this is that premature optimization is actually wasted time. Okay. Now, I'm not completely 100% against optimizing things out of the gate. Good coding practices can lead to more performant code from the outset. So once you have done some optimization work, and once you have seen some of the various libraries and tools that are available to you, as you're designing a new workflow and a new piece of work, you will start to take a hold of these better tools from the beginning. And so often you won't even need to do optimization afterwards, because you've just written good enough code to begin with. And this is not wasted time. So learning good coding practices is not wasted time. That's going to serve you in good stead for many, many years to come. The other thing about good coding practices is that they are almost always language agnostic. So if you learn a lot of good skills about how to profile and optimize Python code and how to write test suites and do automatic testing, if you've learned all of these skills with Python, then they are easily transferable to other languages. So something that I think Adam mentioned in the panel discussion is that you can't optimize to zero. So you're never going to have zero resource usage. The only way to have zero resource usage is to not do the work. So what I'm saying here is that working fast is good, but avoiding work is better. So don't repeat work that's already been done. If you have a particular project that you're doing and you have the capability and capacity to store results, then go ahead and do that, because it may mean that you and other people can avoid redoing those calculations in the future. So repeated computing is wasted computing. So there are two concepts here. One of them is checkpointing, and the other one is minimization, which are good for avoiding redoing work. So checkpointing is essentially, as you get partway through your process, you can save the state of your processing either by generating some output files, or usually by generating some output files or some parameters that are at that point, which means that if your code or workflow needs to be rerun, then it can actually start at that checkpoint rather than having to start from the beginning. So that's a very nice way of avoiding redoing computing work. It's not free. It can take a bit of extra time to implement and debug, but for large simulations, you don't want to have something that runs for a month and then falls over at the last minute because the 2 megabyte output file was writing to a disk that didn't exist. So you'd like to be able to have this checkpointing. This other concept here, minimization, is essentially that if you have functions or pieces of your code that are being called multiple times, is that you have some kind of little cache. And every time that function is being run, it asks the question, has this been run before with the same parameters? And if it has, just return the same result. Don't do the calculation again, just pick up that cache result and send it back again. So these are good ways of avoiding doing work. The way that you implement checkpointing and minimization is a little bit task and sometimes language specific. So I'm going to leave these concepts here for you to explore. We're not going to come back to these. And the other thing I'd like to advocate very strongly is sticky tape solutions. So number one, don't reinvent the wheel. Okay, the number one way to waste time is to write code that already exists. Okay, so you should always try to build on existing solutions. You should use your code, your effort, to move between solutions. And by this, I mean sticky taping together other solutions that already exist. Okay, so you might have a piece of code that's written in C. It does the first bit of processing for you. You then get an output file. Let's say it's a FITS image, and then you want to do some work on that. Well, maybe you've got a bit of Python code that's going to analyze the image and give you a catalog of sources. And then once that's finished, you've got another piece of code that may be a bit of Java that's going to filter those catalogs and remove, spurious detections and that sort of stuff. It's fine to have those solutions independent of each other and to have them in different languages. And all you need to do is to spend your time writing a little bit of bash code that is going to take the outputs of one and put them as the inputs of other. Sometimes you'll need to write a little fairly specific piece of code that is changing data types or something like that. But the key here is to only write new code where none exists. Okay, and one of the best ways to be able to build on existing solutions is that you need to know what solutions exist. And the internet is a huge place. You're not going to be able to, by yourself, find all of the existing solutions. And this is where communities come into play. And so this is where talking to your peers, talking to other people in the field, asking questions on Stack Overflow, going to library repositories such as the Python package index or the CRAN pages. This is where that can help a lot, because you can begin to see what solutions exist that you might want to rely on. And this is one of the reasons why we have the last page in that Google Doc, which is people space for you to list some of the packages or code that you find extremely useful, and potentially put a call out to other people to say, I wish this piece of this particular software tool existed. It's something that does these tasks, and then others can come along and suggest and say, well, hey, actually, funny you should mention that. The thing that you want is already available. And put yourself into contact. The other thing is that there's no one language to rule them all. Okay, in a sense, all languages are equivalent. Okay, any Turing complete language can do any task that any other language can, and so I would say that the goal for you is to choose a language and framework that suits the problem. Okay, so when people say that, everybody will have some favorite programming language that they like to extol the virtues of, and for me that's Python. I'm not hiding that. Everybody will know that eventually. But the key is not to denigrate others who have different choices, because all of the different programming languages have their strengths and have their weaknesses. I would say anybody who only ever uses one language, no matter what, is probably doing the wrong thing. But no matter what your favorite language is, it has its strengths, it has its weaknesses. You as the expert should understand what they are, so that you know when it's a good idea to use that particular tool and when it's not. And then the last thing I say about all of this is optimize only when there's a problem, which I've already said. Just going to take a quick little look into chat to see if there's any questions. Looks like people are just fixing up the installs. Okay, yep. Yeah, I made a mistake with the memory profiler. I put an extra I in the name, so sorry to everyone who ran into that problem when they're installing from the YML file. Yep, okay, cool. It looks like all of the chat is resolved. Good. All right, so as an example, for me, my HPC software ecosystem is the following. So the goal here is to develop a software toolbox so that you can choose the right tool for each of the jobs. And for the work that I do and the systems that I work on, which is radio astronomy, image analysis, and working on the Pawsey system, I use C and Fortran codes for a lot of the heavy compute. I don't write these, but I use code that other people have written. Sometimes that means compiling it. Often it just means module loading from the system. I use Bash a lot for OS interactions and for writing Slurm jobs. So writing jobs that the Slurm task manager can execute. I use Python for sticky tape solutions and coordinating things. So that is to say, all of those little tasks that are they're a bit too hard to write in Bash. Maybe they require some format changes or reordering or filtering of data. I find Python the easiest for me to do that. Once I have more complicated workflows, I use a workflow management system called Nextflow, which is excellent for orchestration. It can talk to Slurm and run all of the jobs that I want. And then ultimately, I use Singularity, I guess I should also say Docker, for portability. So these are two containerization platforms that allow you to install code into a particular container, and then you can port that around. And I find that particularly useful for you developing things on my desktop computer, testing them, and then when I want to run them at scale, I port them across to Pawsey. I say port, what I really mean is copy. I copy that container across to Pawsey, and then it runs on Singularity very nicely. So depending on what you are doing, what your goals are, what your HPC cluster or desktop system is, you'll have a a different software ecosystem. But what I want to point out here is that it's natural to have a range of different technologies that you're using. And often what's going to happen is you're going to be probably expert in one of these things and just kind of okay at the rest of them. And you shouldn't feel bad about that. That's a good thing. Being kind of okay at a lot of different things is extremely helpful in this situation. Okay. So I want to talk about workflows now. Does anybody have any questions or comments about these sort of software ecosystems? Looks like the chat's gone quiet. Okay. All right. Well, I shall continue. So for workflows. So as I said before, a workflow is essentially, in the most abstract case, it's something that maps your inputs onto outputs and it does some kind of activity. Really generically, the activity that's being done is either making decisions, it could be doing some kind of action, or in many of our cases, it's going to be computation. And the input and output could be data, it could be resources, it could be some kind of information. Some example workflows that you're probably all familiar with is one method to analyze data, but also a procedure for reporting OH&S issues. That is a workflow. It's take this form, put this information, give it to this person, they'll perform these actions. Hopefully things, whatever issue it is, doesn't arise again. But I'd consider even things like driving instructions from Google Maps to be a workflow. You're taking some information, which is your desired location and your current location. Google does some figuring out of where you need to go, and it gives you a set of instructions about what you need to do. Another favorite workflow of mine is cooking breakfast on the weekend. So here's my input, the ingredients, activity, it's all of the instructions here, and the output is a delicious breakfast. And the reason I give this kind of simple, easy example here, even though it's not specifically relevant to computing, is to say that you can pretty much think of anything as a workflow. And you don't have to know anything about coding to be able to develop these workflows. So this is something that I like to think of as the astronomy workflow. And this is, the workflow is how to publish papers, because, as much as we love doing astronomy, at the end of the day, publishing papers seems to be the ultimate goal that we're measured by. And so that's the process that we're always engaged in. So we start, talking to people, having ideas, identifying a problem, get a telescope time or computing time or whatever it is, some resource that we need. We prepare an observing schedule. We convert our data into some fancy plot or image. I mean, probably most of the work is here, number 5. We solve the problem because we're that good. And then we write a paper describing steps 1 to 6, and then we publish the paper. Now, this is something that we do a lot of. And as you go through an academic career, this is something that has to happen all the time, often in parallel. So what you would like to do is try and make this whole process as easy as possible to repeat, because you're going to be doing it lots of times. So some of the workflow can be automated or outsourced. Okay, outsourced in this case probably just means collaborating with people who know how to do these things extremely well. So you want to use a particular telescope that you've never used before, you collaborate with somebody and they can do number 4 for you. They can prepare the observing schedule. Typically when you're writing a paper, it's not just you by yourself writing from the first to last word. You've got lots of collaborators that are helping with input there. Similarly, there are other people's code that you can rely on to do all of your data reduction in step number 5. Once you've written at least one paper and you've seen how the whole process works, often the second paper that you write will become easier, and every subsequent paper should become easier after that, because you know ultimately what the final goal is. So the question is, what can you do in steps 1 to 6 to make writing the paper easier? One of the things that you can do is to use standard data reduction techniques, because it means you don't have to describe much in your methods section. You can just say, we used the same data reduction technique as previous paper, citation, there you go, let's move on. Maybe note a few differences. The other thing that you can do is to have very popular or hot topic items that you're trying to solve. That makes maybe not writing the paper easier, but getting it accepted and published easier. The other thing you can do is have clear goals and outputs. Anyway, that's a little bit of a sidetrack. So if you can identify a similar follow-up problem, what could be reused and adapted? So say you've done some work, you've used your telescope, you've discovered a particular phenomenon. You write a paper describing the first of these such things, you make a bunch of wild speculation. Then you come back and do a survey and you're looking to find 10 of these things and do some kind of population modeling to really understand what's going on. Most of the stuff you did before, you're going to repeat. So proposing for the telescope time, you're going to reuse a lot of your content for the proposal. The observing schedule, it's going to be fairly similar. Your data reduction pipeline, you're going to use whatever the final version is. You might write sort of a high level script on top of it that just says, we've now got 10 times as much data, 10 objects, so let's do this thing 10 times in parallel. So a lot of what you're doing here can be reused or adapted. And so that comes to, actually not this page here, which is that the key to success is often having these workflows, and whether they're 100% software workflows or whether they're, at least in your mind, a particular way of doing things, this automation can be extremely beneficial for you and for others as well. So in particular, ideally we want all of our work to be reproducible so that other people can take the same data, do the same analysis, come to the same result. I say other people, and when I say other people, that actually includes you in the future. So the referee comes back to your paper and says, I don't quite trust this result. And you're like, well, okay, I'm going to double check it. So you run it through all the analysis and again get the same results. You're like, okay, fine, I trust it a bit more now. Replicable results is not so much talking about the data processing, but more about the knowledge that you've gained, the science output. So if you get observations of different set of observation, different data set, you do the same analysis, hopefully you get the same results. Anyway, so you also want to have robust and generalizable workflows. But at the end of the day, this is for the benefit of everybody. And a lot of people think about these kind of open, reproducible workflows as something that you do for the benefit of the community. And that is true. It is a community benefit. It benefits science on the whole. But unfortunately, people often think about it as in community things like parks, where you don't have to do any maintenance to it, or any maintenance you do is only for others and not for yourself. But when I say the benefit of all, I'm always including yourself in the future. So anything that you do here for your workflows to make them reproducible, replicable, robust, and generalizable, not only can other people take your work and reproduce it and adjust it to their needs, but you can do that in the future as well. Okay. You might have to swap out a few components here and there, but this becomes one of the available tools that you can then rely on. You're not reinventing your own workflow every time you have a new project. Let me just go back one slide. So what I'm showing here are workflows that people developed during the 2019 Narrabri Radio School. So this is a sort of a week-long event held usually at Narrabri or sometimes at Parks, which is the ATNF radio school. And as part of the kind of data reduction, data processing session, we set a task where we divided people into groups. We gave them each a telescope and we gave them a science goal. So they had to make observations and process data in order to investigate a particular phenomenon. And this wasn't done in a nice way. We didn't say, oh, who knows how to use the MWA telescope, for example. We just gave people telescopes and we gave them science goals and said, build yourself a workflow. And what you can see here is that everybody was able to do a good job of this. These different workflows are operating at different levels. So some of them are extremely detailed. So the one on the bottom right here, you can see that whoever this is in this group has either used this instrument before or has used the software before, because they've got this very detailed workflow, which has a bunch of sort of counterflows and loops. And you can see in red here, they've even identified what type of, like, which software they're going to use for each of the steps in their workflow. But you can also see that there are some other ones, such as the one over here, where there's a few software tools identified, but mostly they're just talking conceptually. What is it that you need to do in order to take your data from the telescope and have it in, I think this says make light curve at the end. So they were maybe looking for variability or something like that. And the point of this is that you don't have to have all the answers before you start your workflow, okay? You obviously need to know what data you're starting with, or what ideas you're starting with and what your desired output is. But you don't have to know every single step of the process, because the process itself is to plan and implement and then update and then repeat. So this workflow on the left here, which I think is far less detailed, will eventually become as detailed as the one on the right here, and probably even more so, because you've gone through that process of understanding how each of the tools work, how they interact with each other, what the best tool for the job is going to be, until you've got to that final step. So one of the reasons why I like this workflow mentality is because it makes you think of your project on sort of a very high level, wide view. And it allows you to think about not only how much time is it going to take me to get this whole thing done, but how much time and how much resources need to go into each of the individual stages. So I like to make a flow chart and to identify dependencies in input output. This particular workflow that's on the right here is purely an image processing workflow, but this applies to just about anything. It is very useful to identify concurrent sections of work. So pieces of work that don't depend on each other that can be done at the same time. And this can either be you identifying things that are computed in parallel, so developing parallel codes or just having multiple jobs running on the supercomputer at once. It also means concurrent sections of work can also mean that you have got multiple people doing different tasks at the same time. In terms of computing here, there's, identify tasks that already like natively use multiple cores or potentially multiple nodes of an HPC. It's good to measure or at least estimate the peak memory use and temporary file sizes for each task. In an HPC, you can request nearly endless amounts of compute time, because compute time is like time. It comes and goes. There's never an end to it. But the things that are hard limits are the amount of memory available and the amount of storage that's available, because they are as installed resources. You can't just request 6 terabytes of memory and hope that it might appear one day, because it's not going to. So it's good to be able to understand what constraints you have on that side. And it's also good to identify here, I've said identify what metrics and plots are required. And for the most part, that means how do you make sure that each of these, in this case, the red boxes, which are the actually do work type stages of this workflow, how do you ensure that this red box has completed okay and that it's worth moving on to the next step? Because I can run this workflow from start to end. I can use a lot of resources, but if I've done something wrong early on, then it's all kind of wasted. All the downstream compute's completely wasted. It's going to have to be redone. So you kind of want to have in your workflow and in your research projects a whole bunch of go, no go, sort of check okay type points for you to evaluate. Am I at the right place? Do I have, is the data at this point, is the project heading in the right direction? Should I continue or do I need to redo that piece of work? Okay. And that, like I said, that also applies to your general work as well. You don't want to get to the end of a 1 year project and then realize actually nobody cares about that science anymore. It's not going to be able to be published. Be good to identify those types of go, no go things early on so that you don't waste all that effort. Anyway, the other thing that's often useful, particularly for compute workflows, is to plan the data movement. So depending on where your data is, it takes a different amount of time to access. So the top 5 things here are all, so the top 4 are all like on-chip memory, which you can, unless you're optimizing the hell out of something, you can largely ignore. But whether your information, whether your data are in memory, by which this means RAM, whether it's on an SSD, a hard disk, or potentially even on a tape archive, you get different access time to these things. So knowing where your data are can be extremely useful, because one of the things that you can do to optimize your workflow is to stage data, separate the data movement from the data processing, so that even though the wall time that it takes you to complete a job might not change very much, the amount of resources that you use can be a lot less. So yeah, separate data movement from data usage tasks. For some systems, they have Scratch or like local on the node data storage, such as an NVMe device, where you should put hot data. So this is data that you're going to be reading and writing a lot, doing a lot of IOPS. And so these file systems have been optimized for that. They're typically ephemeral systems where your data, if you leave it there, it's not going to exist in a couple of days' time. So you need to transfer things off again. But these sort of high performance disks can also reduce your compute time as well. Anyway, so my summary for the data, the workflow section is, in some ways, think about everything as a workflow. Understand that reproducibility is good for science and it's good for your sanity. Portability and adaptability allows you to build on existing solutions. And this is where you're going to get a lot of your time saving. So a lot of your personal time, but also a lot of compute time and resource usage. You can avoid redoing work when you've got this portability and adaptability. I think it's key to evaluate your workflow before you do any optimization. It's easy to guess where you think the slow points or the difficult parts of your code are, in the sense that guessing is easy because you're just guessing. It's more difficult to guess right. And so often what you want is to be able to have some kind of process to identify these slow points or pinch points in your workflow. So the unspoken so far thing is that optimization is great. However, you can't just optimize blindly. You need to actually do profiling to understand whereabouts, how much resources you're spending to do each part of your workflow. And the other thing is flowcharts are cool and fun. So a lot of the flowcharts that I've made for my own sanity, just to understand how my, to plan my workflow, but also to look at it afterwards, such as this one here. At the end of the day, I just threw them into the papers that I was writing, and my data processing section, my methodology section was a lot easier to write because I had all of these nice flowcharts that I could rely on. So, pictures worth 1,000 words and all of that sort of thing. The other thing that I would say about a workflow, if you're thinking about your projects in terms of workflows, at least the computing part of it, that you can then start to, it makes it a lot easier to migrate your workflow into a workflow manager. Okay, so instead of having your own custom scripts which are chained together that are managing the processing of the data, you can start to rely on things like Nextflow to do that orchestration for you, and that takes a lot of the heavy lifting away from you. Alrighty, so let me have a look now. Nothing else in chat. Is there any questions or comments before we move to the next section, I should say? Oh. Okay, all right, looking good. Just double check how we're doing for time. Doing fine, okay. All right, so the next part is all about profiling. So, as I was saying, profiling is step 0 of optimization. Before you can optimize, you need some baseline measure of performance. And as I said before, performance could be any of these things here, stated slightly differently, but essentially it's the same thing. What are the resources that you have available? What are the things that you want to use to measure performance? And this totally depends on whatever the task it is you're performing and the environment, how much resources are available. So depending on your system, you'll have usually a RAM and disk storage cap that is not negotiable. Your time to completion, your wall time is usually also not negotiable, but hopefully it's fairly long. So many systems will give you the option of having jobs that run for at least 12 hours a day or 2 days. There are some systems that have much longer particular queues that are meant for long-running jobs, but you can't just have a permanently running job on a HPC. They don't allow that. And so ultimately, what you need to do is within those constraints, figure out how you can make best use of the CPU to get your job done within the required time. Yes, as I said before, it's impossible to min-max everything at once. And so we're going to have to make choices about which of these things that we're going to measure, which things we're going to measure, and also which we're going to optimize. Now, of course, you can't optimize things that you can't measure. So at the moment, unfortunately, I'm going to have to cross off energy use or CO2 generation because we don't have any tools available that give us that information. Elapsed time to completion, that's a fairly easy timing task that we can do on just about any system. And then the average CPU and peak average CPU and RAM use is something that we can get a hold of. Also the IO reads and writes, something that we can get a hold of as well. So what are we going to focus on? For your home PC, these are sort of the 3 main components that you might want to optimize against. So RAM usage, disk storage, and CPU time. And I've listed here approximately, this is like basic Googling is what I mean by approximately, the amount of power use of each of these components. So the CPU on your desktop, depending on how many cores it has, will use about 100 watts. while it's fully engaged, but when it's idle, it drops down to less than 10. The RAM in your computer is going to use about 5 watts, and it's constant. It doesn't matter whether you're actually reading and writing to the RAM. RAM is a volatile storage, so it just constantly needs 5 watts just to be there. Your hard drive, depending on what it is, whether it's a solid state or a spinning disk, will use about 5 to 10 watts of power. And unfortunately, only about 10% of this is IO dependent. So reducing your IO or reducing your RAM usage actually is not really going to affect the amount of power that is consumed by the RAM or the hard drive. And in fact, those two together are actually quite small in comparison to the CPU. So if we're having a goal of actually trying to use less energy, then one of the things that we can say is, well, let's use less CPU time, okay? Even if you leave your desktop computer switched on all day, hopefully it's not doing work all day. So most of the time it's going to be in this idle state. Right now, when I'm speaking to you, I've got a couple of applications open. I'm not using all of the cores on my computer all of the time. So this is probably in some state between 10 to 100 watts. And that'll be fairly typical for many of the PC systems that you use. Now, of course, when we move to an HPC, this all changes completely because there are way more components to consider. And also, the people who run an HPC facility, they actually don't want their system sitting idle. Because if they've paid $1 million for a whole bunch of compute resources and they're not being used, they're effectively wasting their money. So, or at least this is how they view it. So scheduling systems like Slurm or PBS or whatever else might be used, the goal of those systems is to try and maintain at least 90% resource usage at all times. And so they will take your jobs that have been submitted, they will look at the memory requirement, they'll look at the number of cores and nodes that have been requested, the amount of time that's been requested, and they will slot these things in all together to make some fairly complicated queue, and they'll schedule and run all of those jobs for you. And the goal of all of this is to have a very high usage time. So on a supercomputing system, at some level, your optimization for CPU or RAM or hard drive usage isn't going to affect their energy usage, because if you're not running your job, somebody else will run their job. Okay, so that sounds a little bit sad, but the good news is that if everybody is engaging in this minimal resource usage, it means that the supercomputing facilities don't need to purchase and build as many resources to serve the community. Okay, so me running super efficient code on Pawsey today is not going to affect their energy usage today. But if enough people and enough groups have performant enough code on the Pawsey system today, it means that Pawsey can either delay the rollout and purchase of new systems, or potentially would need the new systems that they buy don't need to be as large and don't need to consume as much power. So as I said, as energy usage may be our goal, if we have this idea of green computing and using less resources so that we're using less energy, so that we're generating less CO2, we're not directly attacking the problem here, but we are attacking it indirectly. This is not completely futile. So as I said here, the focus is therefore typically on less CPU use. But of course, there's RAM and hard drive limitations, RAM and storage limitations that you have to fit inside of. Okay, cool. So the most basic way of resource monitoring is you just open your system monitor on your desktop. Okay, so this is my Ubuntu system monitor. I think I opened Facebook because I know that Facebook tends to chug my computer a bit. So this is showing for the last minute. I've got 4 cores on my, I think it was my laptop. Yeah, this was on my laptop. So I've got 4 cores on my laptop. And you can see here CPU usage versus time. You can see the amount of memory that's being used, which doesn't change. I've got a huge memory load here, mostly because I've got inactive programs in the background just sitting there holding memory. It's a tiny bit of resource of network usage here as well. So this is sort of the most basic resource monitoring that you can do. You can start your program, you can watch what's going on. You can usually see that your CPUs, at least one of them, will max out and probably switch between them. You can also look at how the memory moves up and down. So that's the most basic. It's not particularly useful for like precise timing and profiling because you don't know which parts of your program are using what memory. You've also got this problem in that what you're measuring here is actually system-wide resource usage and not just the program you're interested in. Background tasks typically dominate the RAM usage. So in this case here, this 6.3 gigabytes, I think for my laptop at the time, probably 4 gigabytes of that was me having a couple of Docker containers mounted, running in the background, but actually not doing any work. You also get a bunch of intermittent tasks that give you these weird little spikes in CPU usage, or in this case, the network usage. So you can see in my network at sort of minus 5 seconds, there's this tiny little peak here. I don't know whether that was me receiving an email from somebody or whatever it was. So there are all of these sort of other things that confuse what's going on here. But something you can tell from a system like this is if you find that your program is taking a long time and it's running very slowly, you can open up your system monitor. And if you see that all 4 of your cores are redlining at 100%, then you can say, well, this is a task that is CPU bound. Okay, it just needs more CPU resources to be able to work faster. Or maybe I'm using a really shonky algorithm and I need to optimize that. The other thing that can happen is that, so you can see here in the memory and swap history that I've got the purple line for memory and I've got this green line at the bottom here, which is only 250 megabytes worth of swap. What can happen is if I saturate my memory, if I use more than my 7.6 gigabytes of memory, of RAM, my operating system starts using hard drive as if it were RAM, okay? And that's fine from a program perspective. However, the access speed of hard drives is way slower than RAM. And what can happen is that if you're constantly using hard drive space as if it were RAM space, your program can just be waiting a long time to get the data. So when that happens, you'll see one of these lines move up to 100%, the memory goes to 100%, your swap starts building up to larger and larger, and usually your CPU usage will go down because your CPUs are just waiting for the data to be recalled from disk. So even though this is a super basic resource monitor, there are things that you can do that you can use it for. If I had clicked the processes button here, you can get sort of an immediate view of which processes are using different amounts of RAM and CPU, but you don't get the little plots. I see that Aman has raised their hand. Do you have a question?
Yeah, hey Paul, I use HTOP quite a lot on my computer just to get a estimate of whether I'm using all my CPU resources.
Yep.
And I've been trying to do this on Pawsey basically. And once I submit my job, it goes to a node, and I don't really know how. Is it possible to do something similar on a HPC?
Yes. So when you log into an HPC, typically they have a system in place where you log into what's called a head node or a login node. And that's really actually no different from your desktop in terms of resources. It's probably a high-end desktop, but it's not that much different. And the idea there is it's just to give everybody command line access. And if you type top or htop there, you will see all of the people who have logged in. You probably see 50 versions of VI and Emacs. You'll see a bunch of people doing SSH things and stuff like that. So heaps and heaps of low-level little tasks. When you submit your job goes to a different piece of hardware. So it'll go to a worker node. And in order for you to see the resource usage there, you would also have to log into that node. So on Pawsey, when you submit a job into Slurm, and you can do, if you type in SQ, you can see your job running, and it'll say, it's actually running, and it'll also tell you which node it's running on. And you can SSH into that node. Okay, so on Zeus, for example, it'll say, your job is running on Z051, and you can just say, I want, from the Zeus login, you can say SSH Z051 at Pawsey, blah, blah, blah. And it will allow you to log into that node, and then you can run htop or whatever it is that you want. On systems like Magnus, that's fine to do because typically you don't share nodes. You don't want to, I don't think that your SSH session joining into that node is counted as part of the resources. So if you SSH into the node and use a bunch of RAM in that session, the controller will suddenly realize, actually, these nodes don't have any swap space. Okay, if you hit your RAM limit, the next program to ask for a malloc will be denied and it will crash and die. So you can do this. It's not the best idea, but you can do this. You can sort of do that. Probably a better way would be to run an interactive session using salloc, and where that actually immediately logs you into the particular node that you've requested. You can run your job, let's say you could run it in the background, and then you could do all of your sort of just by hand looking at htop or top or whatever you want, just to see what's happening at different places. Yeah.
Oh, cool. That's basically exactly what I was asking. I've never SSH'd into a worker node, so I didn't know that was possible.
Yeah.
But I do know about salloc, and I'll use that.
I think salloc is probably the safer thing to do. I suspect that being able to SSH into nodes is not recommended. I do it sometimes, but I haven't seen documentation that recommends or otherwise that practice. But I think salloc is probably the safer way to go.
Cool, thanks.
Any other questions while we're at it? Okay. All right, so super basic resource monitoring. We can get a wall time measure. So this is just telling you how long did the program take to run, not how much resources did it use, but just how long it took to run. So there's a bash built in called time, which you can just prepend to any program that you want to run. And it will tell you after the program is run, how much time it took. And it divides this into real, user, and system time. The one that actually makes sense and is useful is the real time. So for the program that I ran here, it took 1.028 seconds. The distinction between user and system time here, and the fact that they don't necessarily add up to the real time, is pages and pages of Stack Overflow and documentation. And I have to say, I've never fully penetrated that discussion, and I don't really know the difference between user and system time, except I guess at the end of the day, this real time thing here is actually a semi-useful measure, which I occasionally use. Okay, so this is how you can measure how long it took to run something. A better timing resource is also available in Linux systems, and it's also called time, but it's not the bash built-in. So you have to access it doing /usr/bin/time. And it will do a similar thing. It will run your task, whatever it happens to be. I've used the -v option here to say verbose. And at the end, it gives me a lot more information. So it still tells me that the user time and the system time, what that is. But it tells me other things such as the % of CPU this job got. And in this time, it's saying 99%, which is excellent. So for this particular task, this particular script that I was running, I've specified I only want to run one core. And this is saying that it's used 99% of one core during that time, which to me says 99% utilization of that one core. So this is a completely CPU bound task. There is somewhere down the bottom here, there's things that talk about file system inputs and outputs, which is something like reads and writes. Unfortunately, or maybe fortunately, because I had already run this before and the file system had already loaded this file, it was already in memory. So I didn't actually have to do any disk IO for this. And so what you see here is that the major page faults are 0, which means that actually I never went and read anything from disk. The minor page faults were this many, which is essentially just the program asking for files which are already in the RAM somewhere. You can see the maximum resident set size. This is essentially the peak RAM that was being used. So this is in kilobytes. So what's that? Like 76 megabytes we used. That's a little bit scary because the file that it reads only about a megabyte. But anyway, that's Python for you. There's a whole bunch of other stuff here that I haven't really got into. But this is actually giving us a much more detailed view of the program. Now, it's not broken down into second by second or millisecond by millisecond, but it tells me only for the program that I'm running. And I guess also if I use multiple processes, it would also tell me for all the child processes. So this is a more precise measure of the program that I want to profile. Okay. All right. So if we want to get more detailed than that, we're going to have to go into some more specific profiling tools. So there's typically two types of profiling tools, and they're called either instrumentation or sampling. Instrumentation is typically where you will you will adjust the code, the program that's being run, either by changing the source code or by adding extra things into the compiled binary. And essentially what it's doing is adding little tiny flags and notification calls that just says, I'm at this point in the code and I'm starting running and I've just exited that function and now I'm about to enter this other function. And so as the code gets run, all of those little messages get passed off to a parent process, which collects those together into a log. And then at the end of the day, will tell you how much time and resources were spent in different parts of the program. This instrumentation approach can be extremely accurate because particularly for the ones that insert things into the source code, you know that you're only measuring the actual code that's being run and not any other code that's being run on the system. The problem is that the profiler itself can actually introduce an overhead because you are actually doing more work. You're doing your original task plus a bit of, introspective work as well. So the programs will run a bit slower in the profiling mode, which means that kind of the best of these profiling tools have a huge effort to be as minimal resource usage as possible. And yeah, It also means that the profiler knows which resources were spent on the program itself and which were being used by the profiler, so you can separate those two a bit. So some examples would include Valgrind or VTune. And so these profiling tools, I think Valgrind is available on Pawsey. VTune might also be, but I've never used that before. The other type of profiling tool is what's called a sampling tool, which is essentially you run your code in the normal way. You don't change the code itself. You don't change the compiled binary. There are no specific little messages that get sent every time you enter and exit the code. But the sampling approach is to say essentially every cycle, so whether this is a millisecond or second or whatever it is, every sampling cycle, this background process monitors the resource usage. So it probably just goes into, so one example would be to go into part of the Linux OS and just say, for this process ID, tell me what is the compute usage, what is the memory usage, essentially like running top, okay? A bit more detail because it can see what pieces of code are being run, what code's being executed, but but you don't monitor, you don't modify the function itself. The problem is that you are running a process in the background, and because you don't have fine control over the process itself running and the profiler running, it's a little bit harder to remove the profiler overhead. But there are some examples include map and also the Linux built-in called perf, which both sampling profiling tools. Now, even though I've divided these tools into two sections, you will find that most tools, most sort of commercial tools will do a little bit of both. Okay, they'll do some instrumentation and some sampling. Let me also say that some of these things are can be language specific. So particularly ones that adjust source code, you will have to ensure that you, one, have the source code, and two, that source code is in a language that's supported by the particular tool. So I think Valgrind is basically C and Fortran and any other derived language such as Python. So they can be quite language specific from that point of view. Sampling profilers tend to be language agnostic because you don't need to actually fiddle with any of the source code. So that's some of the tools that are available. Sadly, we're not going to use any of these because they're so language specific. Our goals for profiling are going to be to learn some basic profiling, and we're going to be using Python as our training language for this. So the things that we're going to be learning is how to time a single function call, how to profile a function line by line so that you're essentially timing not just the total execution, but timing how each individual action within that function is behaving. Hopefully we can do some memory profiling as well so that we can see how each of our lines of code is adding to or removing from the global RAM usage. And we're also going to see some techniques for performant coding, by which I mean taking all of this profiling timing and actually starting to do some optimization work. Now for this, we'll be using Jupyter Lab as a learning environment because I find Jupyter Lab to be extremely good for interactive work and also extremely good for teaching. We're not going to get crazy specific because I want the skills that you learn today to be transferable to other languages. Okay. So I guess partly what we're learning are specifics about how to do this in Python, but also about the methodology and the approach that you would use. And the methodology is what's going to be transferable to other languages and other environments. Okay. So I have a whole bunch of stuff here all about Python. I think, what did I say? I said 2 half-hour, 2 times 90 minutes. So we're at the end of that. I have a huge, big amount of stuff about Python here, which I think is probably fine for us to skip. I would say, let me just touch on a couple of highlights. Python is both an awesome and terrible language for HPC. Some of the cons are that it's interpreted instead of compiled. So pure Python is not really very performant. In fact, the language itself was not developed for high performance. It was developed to be easy to develop and to read. It's not strictly typed, and there is almost no memory control. You can monitor the memory a little bit, but it's very hard to control exactly what Python does with memory allocation. Some of the good things are the focus on readability and development, but also the fact that it's written in C, at least the C Python variant is, which means that you can write Python wrappers to C and also Fortran code. And so most of the performance benefits that Python gets are by doing a little bit of work in Python, wrapping around powerful libraries that are super optimized in C and Fortran. Okay. And it's that kind of link there where you actually really get the best out of Python. You can do multi-processing and multi-threading in Python. So you can do MPI for Pi, which will give you an MPI-like interface, or multi-processing, which is a bit more like OpenMP. The pypi.org has a huge repository of Python packages that you can find ready-made solutions for many of the tasks that you would want to do. This is not a curated package index. It's curated, I guess, in the sense that they've tried to remove all of the, malware, but there's no requirement that the code's actually good. But there is a lot of code there, so you can find some good stuff. I'm going to skip over most of this stuff here. Blah, 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 blah. Blah, blah. Okay. So really all I want is the take-home message is that Python can be fast to develop and easy to code. Jupyter, which is what we're going to be using, Jupyter Lab, is a powerful tool for testing ideas and exploring data interactively. This is primarily how I use Jupyter, for testing ideas and exploring data. Python can be as fast as C or Fortran codes, like with a very small overhead, maybe, I guess, best case, 10% slower. You can make use of multiple cores and also multiple nodes within an HPC by using multiprocessing and MPI for Pi modules. And many of the annoying problems with Python environments can be avoided by using containers. So you deploy all of your software into a container so that it's separated from the operating system itself. So that's, if you want to go back and have a look through all of the Python specifics, you are welcome to do that in your own time. They are not necessary for what's coming up. So what we're going to do now is answer questions if anybody has any. And then we're going to go back to, where's the thing? Go back to the software setup. Because after the break, we're going to get into using Jupyter Lab, and we're going to start to do some profiling, and then we're going to start to do some optimization of Python code. So firstly, questions from anybody? Nope. Okay. I noticed that Isabel's email suggested that we were going to be running from 1 until 4:30 East Coast time, which would mean if we're doing 2 90-minute sessions that we're going to end up with a half-hour break. Yeah, okay, no, that does work out the way I thought it would. So let's break now until 5 minutes past the hour. so half an hour from now. And then at 5 past the hour, we'll start up again, and we will get into the actual hands-on part of the workshop. So feel free to grab some afternoon tea or lunch, depending on which side of Australia you're on. And if anybody has questions or problems, we can address them over the lunch break. Okay, let's see. Yes, thank you, Isabel. That would be excellent. Hello, folks. So I see that Isabel has restarted the recording again. Rather than speaking into the ether, can I get people to, I don't know, do some kind of emote or turn on your video just so that I know that people are back? I'm going to click the yes emote. Here we go. Rebecca, Julia, Isabel, Alexis. Isabel's here twice. Okay, fair enough. John Wan, I can see you. Okay, excellent. Thank you, everybody. Everybody on my screen has done something. All right, so we're back. We're going to get into the more interactive section. So this, hopefully everything's going to go lovely and smoothly. So if we've all done the software setup that I indicated before, we should have somehow installed all of the requirements. So because I've been using Anaconda Navigator for a bunch of other things, that's I've decided to use Anaconda for this install as well. Let me just try and share. I always get the wrong button. I guess I'll just share my screen. It's probably easier because I've got about 50 things to show. Okay, so what I've got, for me at least, using Anaconda Navigator, I can import a new, so if I open up on the left-hand side here, I go to environments, I can see there's the base environment that's always installed, and then there's a couple of other things from other workshops that I've done. And then the ANITA workshop, I created that just by doing import, and then I navigated to the ANITA 2021 Green Computing School folder, which I got from GitHub, and then I looked at the environment.yml file. Okay, so that's how to do it from the interface, the graphic interface. And then if I right click, no, you want to right click, my bad. Yeah, reload later. If I click on the little play button, it'll say open in terminal and a bunch of other things. What I want to do here, so that we all get a fairly consistent approach, is press the open in terminal, which gives me a terminal like this. Okay, so this is just my Windows terminal, but the terminal should have not only who I am and where I am, but also it'll be pre-appended with this ANITA workshop. If you are using Miniconda, or if you don't want to use the UI from Anaconda, you can just go to your terminal and you should be able to type. So from wherever your Green Computing School folder is, you should be able to type in, let me remind myself, conda env create environment.yml. So that will do that. And I believe that Miniconda and Anaconda both use the same syntax here because effectively they're the same thing. So that will create the environment for you. But the thing that you need to do is then activate that environment. Okay, and you should get a, depending on whether you're Windows or Linux, you should get this little ANITA-workshop pre-appended. If you've done your own custom Python virtual environment, then awesome. Pip install, go for it. But I just want to make sure that everybody's at this point where they've got that environment activated. And then all you need to do is go into the Green Computing School folder and type Jupyter space lab. And once you do that, a whole bunch of stuff pops up. Don't worry if it complains about node.js stuff, just ignore that, it's not essential. You'll get a bunch of things here. Now on my computer, what happens is when I run Jupyter Lab, I automatically, in one of my web browser windows, this tab pops up, okay? So this is localhost port 8888/lab, okay? Now, if that doesn't happen for you, then you need to copy this line here, okay? So it'll say HTTP 127.0.0.1, it's the same port as before, and it's got this weird token attached to it, okay? You need to copy all of that into a new browser tab, and then it will open up something that looks like this. Okay, so can I ask if you are not at this stage, if you're having problems, to put your hand up or emote the little cross or some other such thing so that we know that you need assistance. So far, so good. Okay, great. All right, so if you haven't used Jupyter Lab before, quick little introduction. So on the left here, you've got a little file browser that's showing you these are the files that are included in the Git repo. If I drag this across, the things that we are mostly going to be caring about today are these IPyNB files with the little orange icons. So these are the IPython notebooks that we're going to be using. So as well as the file tab, there's also a thing here that shows us what Jupyter Lab is running. So Jupyter Lab can run tabs, which are these ones across here, can run kernels, which are Python kernels, and it can also run terminals. At the moment, that's probably going to be empty for you. If you're looking on the right here and you see that you don't just have Python 3, maybe it also has Python 2. Maybe also you've got Jupyter, you've got Julia or R or some other notebook thing here. That's not a problem. That's cool. That just means that you've got more languages installed than I do. The other stuff here, yeah, forget about those. Okay. So the thing that we want to start with is we want to do the timing and profiling notebook. So if we just double click on that, it should open as a new tab within our page here. And it might take a little bit of time just to start itself up. In fact, what I'm going to do now is, because everything I'm doing now is within my browser, I'm going to stop sharing my entire screen, and then I will reshare just the browser window. I think that may end up being better. You don't have to look at yourselves, and hopefully it's a bit more optimized. All right, I don't know why my computer's taking so long to do this. Oh, that's interesting. I don't know why mine's taking so long. I'm just going to close it down. Start again. Yeah, Python 3. This is weird. Huh. Okay. I've got my own kind of interesting problem here. Maybe I've started this in a weird way. I'm just going to close down my Jupyter Lab and start it again. All right. Close that down. Jupyter Lab. Go. Nope, not that one. This one. ANITA school. Timing and profiling. Okay, there we go. Just needed the good old stop and start to fix it. Who knows why? All right, so you should be able to see a notebook that looks like this. We don't really need this tab that's on the left-hand side here, so I like to just move it away and close it a bit. And I'm going to make my screen a bit narrower so that I can see you all at the same time. All right, so these notebooks are all designed to be very interactive. So if you haven't used notebooks before, there's a couple of concepts to get your head around. One of them is that the notebooks work in chunks, which we call cells. So you can see on the left-hand side here, there's this little blue bar, and that's telling me that I've selected a particular cell. If I double click on this, you can see that actually the cell has just got some text in it. And in fact, this is all just markdown, okay? And you'll see that up here that this cell is of type markdown. So there's a few different types of cells you can have. The ones we care about are code and markdown. When you have a markdown cell, you just type in a markdown language. And when you execute a cell, which you do by pressing Shift Enter or Control Enter, a markdown cell, when you execute, it just renders it, okay? So all of the stuff that you see up here, this is all just markdown. And when we get to an actual code cell, you'll see that the coloring and the background is different, but also there's a little square brackets on the left-hand side here, okay? So we're going to be looking at profiling and timing code in this notebook. So this notebook is just about how to use the timing and profiling tools without doing any optimization. Okay, I have a different notebook that we're going to use these tools to do some optimization. Okay. So the things that we're going to use are what are called Jupyter magics, or IPython magic commands. So, so there is Python, the language. There is then the IPython, which is an interactive Python terminal, which quickly became popular because it added a whole bunch of useful features to the Python console that people like to use. And in particular, it added a bunch of these magic functions, which are actually not part of the base Python syntax. Okay, so anytime you see a command that starts with a single or a double percentage sign, that's indicating that we're using some magics that are not part of the Python base language. Okay, this is sort of an extension on top of it. So you can't use these percent things in your normal scripts that you might want to run. Okay, just in case you get confused about that later on. What we can do, the way that the cells work is that anytime you execute a cell, so for this first cell here, I'm just going to do Shift Enter to execute that. Alternatively, I could actually just press the play button up here that just says run the selected cell. And you'll see that next to the little square brackets, initially they get a little asterisk inside them. And once the execution is complete, it'll get a number. Why is my Windows machine taking so long? That was dumb. Okay, so you can see here it gets a number 1 to say this is the first cell that was executed. And then it also gets an output here. So this particular command generates output, which would normally, you know, if it would normally get printed to standard out or standard error, it's going to appear here in your notebook. Okay, so what's happening here, we're using the time it snippet, which is a little bit like the bash time command. Okay, in that when we run time it and then we give it a little one line of code, what it's going to do is run this one line of code some number of times, usually a fairly large number of times, to try and figure out how long that piece of code takes to run. So it doesn't run it just once because there can be quite a bit of variation. And in fact, what's happened here is you can see that TimeIt has told us that it takes 1.78 microseconds to run this command with a variation of 7 nanoseconds per loop. Okay. And what it's done in brackets here, it says that it did 7 runs, and each run took, what is that, a million loops. Okay. So it executed this thing 7 million times to figure out that that's how long the average, sorry, the mean time to completion. Now, the TimeIt command is quite nice in that if you have something that takes a lot longer to run, it's not going to run it 7 billion times. It might run it 7,000, or in fact, sometimes it only runs it a couple of times. So if the thing that you're trying to run is going to take 10 seconds, the TimeIt command only runs it a couple of times at the most. Okay. Because in order to get its, sort of sub-second accuracy on a 15-minute job, that's kind of not really required. So TimeIt's a little bit smart in that sense there. So what are we doing here? We're just doing a really boring command. We're creating the numbers from 1 to 100 using the range command, and then we're just summing up all of the numbers. And we're not saving that to any variable. That just kind of disappears into the ether somewhere. But this allows us to see that summing over the first 100 numbers is 1.78 microseconds worth of effort by the CPU. You can see on the bottom of my screen here, there's a little thing if I hover over it, and it says one little, looks like a computer chip. So this is just telling me how many things are running. So it says that I've got a tab, which is the one that I'm running, but I also have a kernel. And a kernel is the Python interpreter that's running this code. I'm running Python 3 and it's idle. So what will happen is if I run this again, and you watch down here, it'll say Python 3 busy. It's probably going to take a while as well. Anyway, the other thing that you can note is in the top right that this little circle is now filled in. So when the circle's filled in, it means that the interpreter, Python 3, is busy, or the kernel is busy. And when it's open, it means it's sitting there idle, not doing anything. The other thing you can note here is that I've run this a second time, so now this has got a 2 next to it to say this is execution number 2. Excuse me. So the thing with notebooks is you can execute these cells in any order you want to. The little numbers will increase. So if I run this TimeIt here, this thing will say 3 because it was the third thing that was executed. And normally you would just execute all your cells in order and everything would be fine. But it is possible to go back to a previous cell and re-execute it. And this is something that you would do if you're writing some code and testing it. You write your function, you test that it does what you want, and you realize it doesn't work. So you go back and you rewrite your function, and then you execute that piece, that cell, and you come back and do your test again, and you might go through that loop a bunch of times. So it's normal to have your cells executed multiple times and out of order, but you do need to pay attention when you think you've finished and that everything in your notebook is brilliant. It could be that the current state of the notebook is, current state of the kernel is not represented by the notebook itself, which is to say, until you restart the kernel and run all of your notebook from scratch, you don't know whether you've got a consistent notebook. So I'm just going to put that out there for now because that might be one of the problems that people run into later on. So anyway, so there's the TimeIt command, which just takes a single command, a single line of Python code as input. But we can also use the other version of the TimeIt command that has a double percentage. And the difference here is that the single percentage only works for that line, whereas the double percentage needs to be at the first line of your cell, and it applies to the entire cell. So if I run this, what's happening is it's actually running this entire cell multiple times, okay? And you can see that this one took 377 milliseconds to complete. And in fact, it was only run 7 times. Because of how long it took to run that one version, time it decided I'm not going to run 1 million of them, I'm just going to do one of them, okay? So what's this doing? This is just summing up some other thing, I times -1 to the power of j, whatever. It's doing a bit of basic math, okay? So, yes, okay. So something to be mindful of when we do this time it is that the work that you're doing in here, in these two cases, involve creating a new list of integers and then summing over that list. So every time you execute it, it's doing the same work. In this next bit here, this code is importing the random module. It is then generating a list of random numbers. So for I in range, whatever this is, 10, 100,000? 100,000, yeah. So for I in range 100,000, it's generating a list of 100,000 random numbers. And then we're going to see how long it takes to sort those numbers. Now, there's a bit of a wrinkle here because when you run the sort option, the sort, whatchamacallit? Yeah, the sort function, it actually returns a sorted list. So what happens is the first time you run this, it sorts the list. And then the second time it gets run, the list is already sorted. And so the algorithm is much faster to run on an already sorted list, okay? Which means that it's going to skew your results, okay? So you've got a sort of a larger variance in how long it takes to run. Now, sometimes the time it function will detect that this is the case. So if the first time you run a task takes a while and the second time it takes almost no time, the time it function will also report to you, actually, I think that there may be some results being cached here, okay? So let's try it again. And instead of doing the time it, which just does lots and lots of case, we're just going to use the time function, the time magic. So see here, this ran very quickly because it only did it once. So we printed sorting the unsorted list, so it came into our standard out down here. And the first time that it sorted the list, it took 15 milliseconds to run, which is way different from this 500 microseconds, okay? If we then sort the list again, it took 2 milliseconds. So you can see what's happening here is that every time, so the first time you call it, it actually has to do the sorting. The second time you call it, it actually is just checking whether the list is sorted or not, okay? So, so sort of a bit of a caveat in some of your testing or profiling is that you need to think about whether the algorithm acts differently when you call it multiple times on the same data. So in this case, yes, sorting a list, the time it takes to sort a list is going to be dependent on how disorganized that list is. But other things such as summing over numbers, that's going to be independent of the ordering of those numbers, or, you know, the second time I do that calculation, whether these numbers are sorted or not, it's not going to matter. So sometimes you want to use the time it function. Sometimes you might just want to use the time function. One of the issues with the time function is that, note here how it said that to run it once, it took 2 milliseconds. Whereas back here, when we did the time it said on average it took half a millisecond. So the time function does incur a small overhead in the execution. There's a little tiny bit of startup and there's a little tiny bit of completion. So essentially what this is, it's 2 milliseconds in order to turn on the timer, run the sort algorithm, and do a bit of garbage collection, tidy up some results, and then turn off the timer. Let's see. Yes. So the timer is a bit faster, so it's a bit more clever in that it tries to remove a lot of those system calls and set up things from the timing of it. So you could think about this almost like the timer does a little bit of that. Remember, where did I? Different types of profilers, the instrumentation versus sampling profilers. That's kind of what's happening here, is that the timer is a little bit more like an instrumentation in that it's aware of its own overheads. It's making some smart choices behind the scenes about reducing system calls, or at least excluding system calls from the timing, whereas time is just a sampling thing where it says start now, do the thing, when you're finished, stop the clock. Which you might think is weird, but that's actually why it says wall time here. So it is accurate. The wall time is 2 milliseconds, but that's not actually exactly what we wanted to measure. So we can use time with the double percentage as well. So the same way, just execute that, 478 milliseconds to do that loop. Let's see how that compared to when time it did it. So time it, when we did this before, and we did this over 7 runs, we said it was 377 milliseconds with a variance of 9 milliseconds per loop after doing it 7 times. Whereas with the time function, it says I ran it once and it was 478 milliseconds. If I run it again, I get slightly different results, okay? So I can keep on doing this and I'll get different results. Part of these different results is just whatever happens to be going on in the background of my computer, but there is also some just natural variation between the execution. Okay, questions about the time or time it or these little Python magics? Oh, everybody's happy? Okay. All right. So now we're going to do some profiling of full scripts. So this is probably where we would start for. Usually you start at the highest level. You look at the total runtime of a program and you say that's too long, it needs to be shorter. Then you look into each of the different functions within that program and say this one function is taking too much time. Then you look at individual function or individual lines within that function to see how much time they're taking. And this time and time it magics are really good for just doing those little snippets, okay? Whereas now we're going to look at prun, okay? So let's see. Python contains a built-in code profiler, but IPython offers a much more convenient way to access this profiler. So we're going to use prun. So firstly, we need to create a function, okay? So in this case, this is just a sum of lists. So this is going to say, it's going to do some loop. It's going to create this function, which is j to the power of j shifted. So this double thing here is a shift operator. This probably represents some kind of fancy series, but I haven't had time to think what it is. Anyway, whatever. It's just some basic math. I'm just going to call it basic math. So when we execute this cell, it takes no time really to execute, because all that's happened is we've defined a function. We haven't ran the function, we've just defined it. And Python has said, okay, I've now got a function in memory, which is called sum of lists. If I notice how the cell that I've selected has a blue border and a white background, and you can see the cursor blinking. If I press escape, the border disappears and the background goes gray. There's no cursor, but I've still got this blue bar here. So that's saying that I've selected the cell, and this on the second click tells me that I'm interacting with the cell. So if I go to this level and then I press the little plus button, I get a new cell below it. And so I can start typing I'm going to press tab. Oh, my tab completion, it's slow, that's all, okay. And then Python hopefully gives me tab completion here. So there's the built-in function called sum, and there's this new function that I've just defined called sum of lists. Okay, so that's one way of me to test that my function has actually been defined. And if I just say n equals 5, just a little number, see what it's doing. Okay, it works, runs 40, gives me the result 43. I don't know if that's right, but it's a result. So like I said, what will happen here when you execute this is Python defines the function, and all it's doing is checking that the syntax is right. It doesn't make sure that your function actually works. It's not until you actually run the function that you'll find, oh, I've got some logical errors or something stupid going on. Okay. So anyway, I'm going to assume that 43 is the right answer there. If I select but don't edit the cell, so I go back to this state, if I press X on my keyboard, it'll cut or delete that cell, which is what I'm doing now. So now what we can do is we can use this P run. Sorry that I keep on selecting that. And I'm actually going to reduce this, because when I did this on my computer before, it took forever. So I'm going to run this 10,000 times instead of 1,000,000 times. So if I press Shift Enter, oh, that was pretty fast. Okay, maybe I'll run it 10 times longer than that. Okay, 100,000 times. So what we're getting out here is that the sum of lists, prun, it looks like it called my function 14 times. And it's telling me these are the number of times a particular function was called, and the total amount of time spent doing that. So over the 5 calls, the amount of time per call. So for a single invocation, this is how long it took. The cumulative time, which is not the same as the total time. Why is that? Not sure. And then the per call time again. That's weird. Okay. Yeah, these columns were very much the same on my Linux machine. Oh, they're different here as well. So it's a little bit tricky to interpret what's going on here, because it is looking at the individual operations that are being done, and then it's ordering them by how much time they took to execute. So if you look really carefully, you can see a few things in here. So one of them is this option, which is saying the built-in method built-ins.sum. And that is here. We've only done it once, so it's easy to identify. And the sum command took 0.001 seconds per call. Some of the other things, so here there's list comprehension, which is this bit here, which is where you use the square brackets and you say you define this value for j in range. So list comprehension is kind of a Python way of shortcutting a loop. So instead of writing a loop, you can just do it all on one line with this list comprehension. What else is there? There's an exec, there's a profiler. It's kind of a bunch of stuff here that if you really dug into the Python language, you could probably understand it a bit better. But it's not quite doing what we want, okay? The bulk execution time is in the list comprehension inside sum of lists. Oh, I see. Go. All right. So there's a lot of options for prun, and if we want to see what they are, so I'm going to press B to create a new cell below the current one. And if I type prun ? And I execute that, that actually gives me the doc string or the help for that function. So this tells me I can, there's a bunch of options that I can use. Okay, the options include a whole heap of stuff. Holy crap. Yep, there's a lot of options. All right. But ultimately, this profiler is not particularly useful by itself. Usually, you will have wrapper programs that run this profiler and then interpret all of the output from it. So I'm just going to kill that cell. So we're going to use something a bit nicer, which is a line-by-line profiler, which actually maps the execution time to each of the lines in your code. Okay, so we're going to load the line profiler extension. We do this just with the another Python magic load extension, line profiler. So this is almost like doing module load, or sorry, not module load, import. This is almost like importing a Python module. But when we do this load ext, it's actually loading not just the module itself, but a bunch of the additional Jupyter magics, okay? Which means that not only do we have the line profiler module, we also have this new magic called LP run, okay? So LP is the line profiler, okay? So let's have a look at this. So the way that we do this is we say LP run, and then -f is instructing LP run, just telling us which function we actually care about, okay? So we have to say we want to profile the sum of lists function, and then we want to execute the following code. Typically, it'll be the same. It'll be execute sum of lists with some input and profile just the sum of lists function. So if we execute that, all right, if we execute that, we get something that at least I find a lot easier to read and interpret. So it says here, timer unit, 1 times 10 to the minus 6 seconds. Okay, fine. This is the function that's being profiled. And what it's doing now is it's showing us for each line of the code, how many times it was hit, which means how many times it was executed. Okay, so total equals 0 was executed 1 time. This is how much time it took in total to execute, and this is how much per hit when you average it. And then this column is the one that I usually focus on. It is the percentage of the total time spent. Okay, now these numbers here, this column, is all multiplied by the time unit of 10 to the minus 7 seconds. Okay, not so interested in the absolute values, just the relative values here is what we care about. So you can see, of course, this only gets executed once. This is a loop that goes from 0 to 5, so 0 to 4, so that everything in the loop gets executed 5 times. You can see here, executed 5 times. The loop iterator always gets executed 1 extra time. Why would that be? Does anybody know what?
Is it not verifying that the condition is now false?
Yes. So to start with, this is like saying, you know, for I equals 0, I less than 5, I plus plus, right? So it's for the first time, it sets it to 0, keeps on going around. Once these have all executed 5 times, it actually returns to here and says, actually, I don't have any more work to do. So your for loops and while loops will always have a slightly higher hit rate, usually only 1, than everything else inside them. And as Reinhold said, it's because it's checking the exit condition, essentially. And then the return function, yeah, the return is just, it's free, okay? So what we can see here is that this function has spent 97% of its time doing this piece of work. So if we were to try and do some profiling, what I would want to do is try and make this line take less time to run, okay? The other things we can just ignore, at least for now, okay? Let's see, this is how it was for Jake when he built this notebook. He got effectively the same answer, okay? Let's see, anything else I need to say there? I think that's about it. I guess something else to note is that here it tells you the function. I can actually have, so let's say here, the sum of lists, instead of only executing that, I could say maybe my code has a little bit of initialization work that needs to be done. So I could say n equals 5,000 and then run n of lists on that. And what it's going to do is it's still going to execute all of this code. It's just that this is the only bit that needs to be profiled. So maybe my initialization step is load a piece of data and then run this code and then clean up after myself. So you can have a fair bit of stuff in here, but you're telling LP run that you're not profiling the loading or the cleanup. You're only profiling just this sum of lists. Okay. So let me just turn that back to what it was. All right. I think that's all. Is there any questions about this LP run? Okay. You would probably, when you're doing the testing, so this is coming back to, I think it was Ollie's question before about, what's an appropriate test size for testing. So if I ran this only 5 times, so the loop was only length 5, we would see that the distribution of timing changes quite a bit. Okay, so now we're only spending 60% of our time doing this bit of work, and these other parts of the code start to become more significant. Okay, and that's, at this point you would still say, okay, spend some time optimizing this, but it would be less of a priority. So when you do your testing, you still want to keep in mind, how is this going to be used in general? Because typical behavior of many algorithms is that they have a particular scaling performance, and some algorithms that are really, really highly performant for large data sets are actually have a fairly significant overhead for small data sets. So some like database indexing algorithms, when you run them on a small data set, it's actually takes longer than just doing a normal, like, listings, just do like a bubble sort or something like that. So your different algorithms have a different scaling, and it means that there will be different regimes in which, depending on either the data size or in this case, just the number of iterations, as to where you would need to focus your optimization efforts. So it is important that at least sometime during your profiling is that you have a profiling on a real world representative test case, so that you can, you're not being misled. Okay, so let me just put that back to 5,000 again. Okay, all right. So let's go to the next one. So the next one that we're going to use, we're going to look at, is the memory profiler. Okay, so if we load the external thing again, so load ext memory profiler with one I, despite what I wrote earlier. And then we're going to run this sum of lists again, but we're going to run it for, how many times is this? This is 1 million, okay? So we'll run this and we'll see what happens. Hopefully my computer doesn't explode. Oh, okay, that worked fine. So what it's saying here is that when I ran this sum of lists, at the worst, the peak memory usage was 144 megabytes, and that represented an increase of about 60 megabytes over what was already being used. Now, the memory profiling is a bit difficult because this peak memory actually is not just the memory that was created because of my function. The peak memory is how much memory is being used by the Python kernel. Okay, so that includes all this other crap that I've computed before, anything that I've imported, so importing modules will add code and data into the memory. So anything that I've done in my notebook previously still exists in the interpreter memory, including the output of all of it. So all of these outputs here, these are also stored by the Jupyter Lab session. In fact, you can even access those. So, so this 144 megabytes is a bit deceptive, but what's really important is this increment here. This is saying that by running that piece of code, you increase the memory usage by 60 megabytes. Now, let me run this again. It's a slightly different number now, okay? And what's happening is that in the background, Python is doing its own memory allocation and deallocation. And a bit like Java, Python has a garbage collection routine that hangs around in the background, tries to identify bits of memory that aren't used anymore, and then deallocates them. But the Python garbage collection service is a little bit picky. And as far as I can tell, sometimes it really wants to just hang on to memory because it thinks you might need it later, even though you're not accessing those particular objects. It wants to hang on to it and reuse it because it's faster to reuse memory that's already allocated to Python as opposed to mallocing stuff from the operating system. So anyway, so this changes a little bit. So this is just using the memit, which is a bit like the timeIt. If we want to do some more detailed memory profiling, in this case, we use MP run instead of LP run. So LP is the line profiler, MP is the memory profiler. The difference here is that the memory profiler can't run on code that is in memory. It has to run on code that is in its own file, which is a bit annoying, but this is how we get around it. So this piece of magic here says that the following cell will be output to the file called mprun-demo.py. So if I execute this, it says that it wrote that file. If I look in my little file thing over here, if it refreshes, mprun-demo. Okay, so I've now got a Python script and I can open that up and it just, oh, there you go. That's exactly what I had in my cell. Okay, so what that's doing is saying, write all of this to a file. Unfortunately, it does not also execute that code. It only just sends it to the file, but that's fine. So now what we have to do, if we want to profile this function, we have to import that function. So from mprun-demo, which is the file, we import the sum of lists function. Okay, this will replace the one that's already in memory. And then we can do the memory profiling. So again, we do -f and we say sum of lists because that's the function name that we want to profile. And then in here, we're going to say, let's run this with a size of 1 million objects. So let's see how this goes. Yeah, this is the bit that took a while on my computer for some reason. There's some example output here that I can talk through if this doesn't complete in a nice amount of time. I don't know why this takes so long. Does this take a long time on other people's computers, or is this just a me thing?
It's still running for me too.
Yeah, okay. All right, well, we can see that the kernel is busy. All right, should I do that? All right, well, the output's going to look eventually something like this. So let me just describe what's going on. So what we want to see is, again, a line-by-line breakdown of the memory usage. So this time what we've got here is this is the resident memory for the Python kernel. And these numbers here will be different from yours because this is just what happened whenever Jake ran this notebook when he was creating it. And then the interesting part here is the increment. So assigning a single integer gives you 0 megabytes of usage. There are options here where you can change the increment to be in kilobytes or in bytes, but I would say anything under a megabyte, who cares? This I in range. So somehow the for loop is using is allocating 7.5 megabytes worth of memory. I'm not sure I understand why that's the case. This list comprehension is allocating 25.4 megabytes of memory. And this I do understand because what's happening here is that inside this list comprehension is a loop that goes up to 1 million entries, which is doing some computing, but essentially you end up with a floating point number. So this is creating a list of 1 million floating point numbers. And that, at least on this system that it was tested, took 25 megabytes worth of memory. When we do the summation, actually, we're just changing memory values. We're not allocating new memory. And then at the end here, we're actually deleting the L list. Okay, so we create a new list by adding and add 25 megabytes. Here, we delete that list, which means that the increment is now negative. Okay, and then when we return out of our function, behind the scenes, Python goes and unallocates all of the other memory that may have been used that is no longer referenced. So whatever was being created here when we started our for loop is now deallocated. Okay, so what this is telling us is that this list comprehension, or rather creating this very long list, is using a lot of memory. Thankfully, 2 lines later, we deallocate that memory again. My thing's still, oh no, it did finish. Holy, what? No, there's something wrong here.
I have the exact same thing.
What? Oh, I don't think I even have that much memory on my computer.
Me neither.
But yeah, no, that's wrong. Okay, there's something wrong. There's something wrong with my system. It's deallocated more memory than I have. So something wonky going on there. And again, I don't know why it's got that many occurrences. I think the list comprehension has somehow confused this. The memory profiler. Okay, that's very weird. Anyway, we shall continue. So I will say that memory usage in Python is extremely difficult to control. I mean, on one hand, it's easy because you don't have to do anything. You can use this del operator to delete an object, or at least remove references to that object. So what that's saying is that this variable L no longer refers to the memory space associated with this data here. So if you remove all the references to an object, Python will eventually deallocate that memory. But there isn't any way to tell Python, this object here, please kill it, do a really hard kill and expunge it from memory. And if I happen to want to use it later on, maybe you can throw an error later on. There's no way of doing that. You can't just dealloc or memfree or whatever you want in Python. Everything goes through the garbage collection. So my advice is that if you're using Python, that the best way to reduce your memory footprint is to just not allocate memory in the first place. And depending on how you're doing multiprocessing and whatever, there's different ways to that you can do that. Anyway, but because the memory profiler is a little bit balked, and because memory is so hard to control in Python, that's about all we're going to do for the memory profiling. So what we're going to do now is move over to the optimization workbook.
Paul.
Yes, question.
Sorry to interrupt. Before you move on to this, so in like C++, you can set your integers based on how much space you want to give them. In Python, you don't do that. Is Python clever enough to, for some of these numbers, they're going to get pretty big. Is Python clever enough to request more information as it gets to these bigger numbers?
Yeah. So if I say a equals 0 and then say what type is a, it'll tell me it's an int. And if I say a equals that, and then it now tells me that it's a float. Actually, I think that's a float by default. Yeah, so Python it doesn't have strict typing, and it will do like behind the scenes typecasting. So if I've got 0, it now tells me that it's a float instead. I think because this is Python 3 and because my operating system is a 64-bit system, these are all float 64s. Okay. Python doesn't necessarily make the smartest choices. So it won't allocate 0 and say, oh, 0 could be stored as a Boolean, so I'm going to store it as a Boolean. And then when I say a equals 3, it won't upgrade it to a short and then upgrade it to a long and then upgrade it. So it won't do that sort of thing necessarily, except to say that integers will be 64-bit integers, floats will be 64-bit floats. If you want something that is uses more than a 64-bit integer or float, there are kind of extension types in Python that you can use. So you can say, I explicitly want this to be a 128-bit integer. And some of the Python libraries will respect that, but many of them will just cast it back to a 32 or 64-bit float or int. So in fact, one of the problems that I have with some of the code that I'm working on is that the data that are stored in a FITS image are 32-bit floats. Okay, so I have a FITS image where each pixel is a 32-bit float. When I load that onto any modern system with Python 3 using, let's say, NumPy, for example, it will automatically convert them all to 64-bit floats. So it immediately doubles my memory usage. And then when I write that back to disk, it will write 64-bit floats. So sometimes you have to do that explicit typecasting in Python, but it's a bit finicky and annoying to have to do that all the time. So in the case that I just mentioned, I settled for load the data, do all the processing, don't care that it's 64 bits. And then when I go to write the data, cast it back to 32 bits and then write it into a file. So that was the sort of compromise I had to make. Because some of the Python libraries will allow you to specify the data type that you want your answer to be returned in, but not all of them do. And so that means that most of them just end up giving you 64-bit, whatever the platform default is, 64 or 32. Yep. Further questions? times. Okay. So I'm going to close, actually I'll keep it open in case we need it. So I've just opened the optimization activity notebook. This is a new Python kernel, and so it doesn't know anything about my other notebook. In fact, the kernel I don't believe has even started. Oh no, it has started. Okay, I was wrong. So I'm going to just close these little bits here. All right. So I have an example here, which is deliberately trivial, which is we're going to time and profile a matrix multiplication code. So Python has a built-in type, which is a list, but Python does not have arrays. Okay, it doesn't have multi-dimensional arrays as an explicit type, which means that when we want to represent things like matrices, people will often do this list of lists approach, which is to say that my matrix is a list of 3 items, and each of those items contains 3 other items, and those items are actually integers that I'm interested in. So this is how we can define a matrix in pure, like, base Python built-in types. And so we want to work with those types for our initial instance of the code. Okay. Now, there are no helper functions that allow me to construct large matrices like this. And so what I'm going to do is a little bit of a sideways cheat, and that is that I'm going to use NumPy, which does have matrix and array built-in types. And I'm going to use NumPy to create a random array. So I'm going to create a random seed so that I get the same array every time. I want my matrix to be 50 by 50, and I want random integers between 0 and 10. Whoops. In a 50-50 matrix, and the same for my matrix B. And because I'm lazy, I'm going to also compute the matrix multiplication of those two things. Okay, so this is all using the NumPy library, which we're going to return to at the end. But what I really want is actually not NumPy data types. I want Python data types. Okay, so if I execute this cell and then I say, what is A? It will say A is a list, which is good. And if I say, what is A element 0? It is a list of 50 integers. And yeah, that looks like 50 to me. Okay. So I should have, if I ask for len A, it should say that I now have 50 of those. There are 50 lists within it, and the first list has a length also of 50. Okay, so that's what I want. Okay, B and C are going to be the same. So what I've set up here is my test data, A and B, and my validation data, which is C, which is the multiplication of these two things. So now that we've got our test data, we're going to write our matrix multiplication function. So our goal is to compute this. Okay, so we've got the matrix C, element ij, is the sum over K of matrix A and matrix B. Okay, which means if we want to compute this matrix here, we need to do this for every value of I, J, and K, which means we need a three-way nested loop. So let's do our very basic matrix multiplication. This is going to be, I'm going to append an underscore number to each of my functions because we're going to create a few of them. We also want to check that the input data are correctly formed as well. So there's a bunch of tests here to say, do you got the right rows and columns? And if they don't match, just skip out early, don't do any work. Then we create our initial matrix for C. So this is equivalent of allocating memory. This is a double list comprehension, which just says, make something that's all zeros and it has the right shape. And then we do our triple nested loop. So for each of the rows in A, for each of the columns in B, and then for each value of k, we do this computation here. Okay, so this is a very explicit, pure Python implementation of matrix multiplication. Okay, and what we want to do is profile this and see which bits are fast and whether we can make it any faster. Okay, but before we do that, it is good practice to write a little function that tells you whether your like little piece of test code here to tell you whether your optimized function is actually even getting the right answer. Okay, so my function is called correct. You feed in the two matrices, you feed in the answer and then the function that you're testing, and then it will tell you true or false whether the multiplication agrees. Okay, so I'll tell you now, you can get really excited with your profiling and optimization and think that you've got an amazing solution, only to find out later that you have a really, really fast way of getting the wrong answer. So make sure that before you profile and test before you profile your code, make sure it's giving you the right answer. Okay, otherwise you're just wasting time. So let's see how long it takes to do this matrix multiplication. And this, on this computer, it says that it took 38 milliseconds to do that multiplication, which, okay, that's fine. So now let's try and do some optimization. Let's see if we can reduce that time. So what we've seen here is that this piece of code, which is the inner part of our loop, okay, this is where pretty much all the work's being done on this line of code here, is making repeated read-write access to an array element in C. So this plus equals means C equals C plus A times B, which involves two lookups because we've actually got a double nested list here. Firstly, it has to use the I index to find the outer list, then the J index to look inside that list to find the value that we're going to update. And this sounds like a bad idea. So let's see if we can refactor that so that we don't have to keep on accessing this C matrix in this way. So what we'll do instead is we'll use some temporary local variable called n, and we'll sum over it. We'll just use that as our accumulator. Okay, so we'll accumulate all our values onto n. This is a local variable. This doesn't require any list index lookups, so it should be fast to access. And then once we've done the accumulation, we can then assign that value to C. Okay, so that's avoiding all of those lookups. So let's define the function, and then we can actually test that it's correct. Yeah, it's correct. And then we can do the timing. And did it help? 29.1 milliseconds versus 38.2. Yeah, okay, so that made things better. So it looks like we're on the right track. The other thing that we can do is let's get away with that temporary variable altogether, and let's collapse one of our loops using a generator function. So what's happening here is we want to create a generator that returns the AIK times BKJ for each K result, and then we want to sum over that. So what we do here now is we replace one of the loops with this generator function. So this still makes only a single assignment to the CIJ. And in fact, we don't have to read from it anymore. We only have to assign to it. And here we're doing this list comprehension to kind of cheat our way out of that loop. Okay, so this seems like a fancy, maybe super optimized way. Let's give this the right result, could be good, of doing things faster. Okay, we do our time it and 33.7 milliseconds. Let's see, slower than when we used a triple nested loop with a local variable, but it's faster. What's that, 38 versus 33? It's a little bit faster than the original implementation. So we're kind of, yeah, sort of going in the right direction. let's get a little bit crazy and turn all of our loops into list comprehension. This should be really awesome. Okay. Also, instead of doing this list comprehension, which sets everything to 0, we don't need to do that anymore. So now I've replaced this entire function with just this one list comprehension. Now, it's not obvious that this is going to work, so I need to test. Oh, and it worked. I do my timing. 32 milliseconds. This isn't really going so well, is it? No. So we've mostly just been working on guesses as to what we think might be the right thing, but we need to actually do some profiling to see where the slow points are. Okay. So we'll load the profiler and let's profile matmul2 and matmul3. And I guess I should also profile matmul1. So I'm going to add a new line below. Paste that in. matmul2, profile that as well. Okay. So now we're doing some actual profiling and we can see, now we can actually tell where the time is being spent in our function and what we should be optimizing. Okay, this is what we should have done to start with, is firstly profile and then start the optimization process. So turns out, where are we? Matmul1. Why has this got? That's not matmul. Oh, sorry, 0. 0 is what I was looking for. Okay, this is the original one. So according to this, most of the time is being spent, yep, okay, just doing the calculation and assigning the value. A lot of time is being spent here, but weirdly, not much time is being spent in these two loops. I'm not sure I understand why that's the case, actually. Oh, yeah, I do. Okay. Because this loop, individually, here we go, per hit, 6 or 7 times 10 to the minus 7 seconds, but this inner loop gets run. It gets run 127,000 times, which is why it seems to take up so much time. Okay. We can look at our other line profilers. So this is the one where we just did the list comprehension. We removed one of the loops, which seems like it's good. So now we've focused all of our time into this one thing here. And in fact, if we go all the way to our final one, matmul3, this is telling us that 100% of our time is spent doing the work that we want. So that sounds good, but it's a bit of a pain because by doing all of these, what is effectively a triple nested loop on one line of code, of course, all of our work's being done on that one line, but we don't really have any clues as to how to speed that up. And in fact, from the timing that we saw before, the conclusion is that the Python loops are already really fast, and that by doing list comprehension, we're actually not making things noticeably faster. But what we are doing is making things harder to read, because even for me, who is a many years seasoned Python programmer, this thing here, I can tell that it's a triple nested loop, but it's not always obvious to me which order these loops are being done in, and which what was it? Yeah. What it's actually doing. Okay, so yeah, sure, it seems like matrix multiplication, but it's removing the readability of the code. It's not making it faster, and it makes it harder to profile because all the work just gets done on one line. So yeah, conclusion, Python loops are fast. List comprehensions can be useful, but they don't give you much of a speed increase. And in fact, what we should have done is just not use pure Python code. We should look at some of the libraries that actually do this manipulation for us. So let's make a new function, which is just copying the NumPy multiplication function. Does it give the correct result? Well, of course it does, because that's how we calculated the result to start with. And let's do some timing and see how long it takes. And on my Windows machine, it takes 587 microseconds instead of the milliseconds that it was taking with the other code, which means that the NumPy implementation of this function is order 1,000 times faster than the pure Python version. And this is because NumPy is not using pure Python, it's using C-level libraries, which depending on your system will use some of these highly tuned linear algebra libraries in the background. So depending on what system you have slightly different libraries, but NumPy will choose the right one and it will use that where it's available. So you can see it took microseconds, 500 microseconds. Now, NumPy actually, even though it can work with these AB things, which are Python lists, NumPy really excels when you use NumPy data types, because NumPy data types are essentially C data types with a little bit of Python wrapped around them. So let me make these new arrays, D and E, which are just NumPy versions of A and B. So if I say here, let's look at the type of D, it'll now say numpy.nd array, as opposed to the type of A, which is just a Python list. Okay. So by using the numpy data type, let's do this timing it again. And we will see. Don't know why my computer's so slow. It's not so much difference, but anyway. So it used to be 580 microseconds, and now it's only 155 microseconds when I use the correct data types, or when I use the NumPy native data types, which is actually telling us that the overhead in converting the Python list to an ND array is significant. In this case, it's about 400 microseconds, which is actually greater than the time to compute our result. Okay. So second conclusion is don't reinvent the wheel. Look for the extensions. All right. So that was the first task. The next task, I would like to suggest that for this task, I'll go over the idea of what we're doing now, and then give you some time between now and next week to actually dig into some of the optimization here. Have a go at trying to write some really nice optimizations for this function, or to at least profile it and understand what the limits of optimization might be. Okay, so we'll start now, and then this will be our sort of kicking off point for next week. So this is code that I wrote a few years ago before I learned all of the above lessons. All right, so it's not intentionally bad, it's just accidentally not optimal. Okay, so the task is something called sigma clipping, which is where you take a list of input values, you calculate the mean and standard deviation, and then any values that fall outside of that standard deviation, whatever it is, some range, get removed from the list, and then you keep on iterating through that process until you have a stable list, okay? Until you're not removing any more items. And for the purposes of the code that I was writing, it was important that infinite and not a number values were allowable inputs, okay? This had to be a piece of code that would allow you to use those inputs, but they should be ignored, okay? So we're going to set up a bunch of data as our input. These are just two lists. These are lin space, so this is just uniform spacing of data between 9.5 and 10.5, and then another one between 0 and 20. We're going to set the first one to nan and the last one to infinity. And then the code, the Sigma clipping code, firstly removes all of the not finite values. And then it just goes through this loop of continuously calculating the mean and standard deviation, removing values that are outside the low and high bounds. And it does this until one of the iterations is no longer removing values from the list, or until the list is 0. Okay, so we'll define that function. And we want to compare this to a nearly equivalent function which is provided by SciPy. So this is me trying to reinvent the wheel, being silly. So if I look in the scipy.stats package, there is a function called Sigma clip. And if I look at the help, so if I press Shift Tab, I should get inline help for the scipy.stats.sigma clip function. And it tells me what it does and what it returns. And what this does is Sigma clipping, but what it returns is the array of values and then the lower and upper bound factor. It's not quite what I want. What I want from my other function is the filtered or clipped array, but then I also want the mean and standard deviation value. So, and the other thing is that the SciPy version of this code, if you feed in nan or infinite values, your return values, the upper and lower will just be infinity, and it won't clip anything. It's not intended to be used with nan values. So in order to compare my code with the SciPy equivalent, I have to write a little wrapper function. Firstly, which clips the data and removes the not finite values. And secondly, once you have the clipped data from your Sigma clipping, it then needs to calculate the mean and the standard deviation to return them. Okay, so what I'm comparing here is my code where I do everything myself to this code where the main hard work is being done by the Sigma, by the SciPy package. I then want to write myself a little function that compares the two, compares any two functions to make sure that the mean and standard deviation and the returned arrays agree. And then I'll do my first little test. So with the data, with the Sigma clipping of -2 and 2, they all agree. So then we can do some timing, how long it takes my version to run and the SciPy version. So this is our baseline. Okay, so we can see we're actually not that far from the SciPy one to start with. So here, my version of the code is 300 microseconds to run, whereas the SciPy version is 230 microseconds. What I should do here is make my data array much larger, because this has 36 values in it, whereas typically the data that I would be running this code on would have about 10,000 values. So in that respect, this is not necessarily a good test, but for the purposes of this workshop, it's good enough. So this is where you come in. To run the LP run on each of the two functions. So let's continue using these parameters, the 2, 2. So run that on the Sigma clip and on the SciPy wrapper function, and have a look at where these functions are spending their time. And then after you've done that, I've got some suggestions here as to places that you might want to look at some of the optimization. Okay, I've just copied the code here, but it's up to you to do the optimization in this part. So I think because we're now at the end of our allotted time, I would like to finish here, leaving you with some of this, I guess you could call it homework, but at least to have a think about this, look at the line profiler for each of them, understand which one you think is the fastest, which one would be easier to develop, as in if I asked you to change it, how easy would that be? And which is the easier to maintain. So let's just say that there's a Python 4 that comes out and I tell you, you need to port all of this code to Python 4. There's a bunch of syntax changes that need to be made. Which of these do you think might be easier to maintain into the future? So that's where we're going to start next week, with a bit of a discussion of that. And then we're going to get into the optimization practice a bit. So if you can have an attempt at that, at least just one go beforehand, but we will have time during next week's workshop to go through some of this optimization. So I'll leave it there and open the floor to more questions. If anybody has questions. Where's my chat panel? There it is. Okay, I see people have different timing results. Let's see, this was for the map mole. Okay. Yeah, I think what's happened here is if we make our matrices a lot bigger, so instead of 50 by 50, let's do 500 by 500. We don't need to redefine any of our functions, but we can redo the timing. So between different systems, we're probably more likely to see a consistent behavior with larger data, because I suspect that what's happening is that we've got different system overheads that are in place. Of course, this can take forever now. Map mole 1, oh no, not that. Time number 1, time number 2. All right, see how we
Paul.
Yes.
In the first iteration of that function that we wrote, we were reading in we were doing the IO on the CIJ, and that's why that one took longer. But the later iterations, we don't do that. We still IO on all the other things, but we're sort of just condensing the for loops into tighter and tighter list comprehension. I'm not sure I understand why we would expect that to be faster. What's changing in the back end that means that a list comprehension should be evaluated faster than a for loop?
I wasn't saying that this was a smart choice. I was just saying that this was in some ways meant to be an example of, I think it should be better and therefore I'm going to go ahead with it, as opposed to I've actually done the profiling and found that this is the problem and therefore this is what my new solution is going to be. I think part of it was inspired by, if you're doing like in a lot of compiled languages, if you write your for loops in a particular simplistic way, then the compiler itself can do some sort of smart unrolling of those loops, which can avoid the constant incrementing of your whatever you want to call it, your loop iterator. Won't have to do constant checking whether against the end condition, all of this sort of stuff. So in some languages, replacing for loops with something like a list comprehension can actually give you a performance increase because the compiler does the optimization for you. So that's something where a lot of people have this idea that in Python, list comprehensions are faster. The truth is they're not faster. It's not a compiled language. There is no compiler optimization that happens. When you write this thing here, Python is in the background just doing the same for loop. That's all that's really happening. There is a little, maybe slight optimization, but in particular for Python 3, Python 3 really tried to make it so that list comprehension and loops had the same performance. They optimized the Python loops as best they could. So I think if you were to try and use, if somebody's got a Python 2 notebook, then this might have, oops, oh, my camera is completely dead. That's lovely. If you're running Python 2, then maybe you would have seen some different results. So yeah, so I'm not saying that was something that should have worked. It's just a common idea that many people have, is that using these really obfuscated kind of list comprehension is making you a pro and making your code faster. That's all.
Got it. Thank you.
Let's see if my thing's even finished yet. Yeah, I don't know what's going on here. My 500 by 500 matrix is not finished. So we'll see. I don't often run Python on my Windows machine, and it's a very old Windows machine. So yeah, I'm just gonna blame that. For now, so if you've got a cell that's just running for a long time and you want to kill it, you just press the little stop button, and it interrupts the kernel, and it gives you error messages because you interrupted it. But whatever, it's finished. Yeah, so there will be system dependent overheads that you have to deal with. Just try with 100 by 100 and see if that's not crazy. Oh, there we go. Still 300 milliseconds. And this one is 229, and this one is 257. Okay, I'm getting pretty much the same ordering as that I did before. Yeah, okay. Okay, are there further questions that people have? More discussion topics? Nope. I see that people have been filling in their go-to cannot live without libraries. Thank you for doing that. Despite our focus on Python, I'm glad to see that people have also put in some R packages, and I encourage you to put in other language libraries as well. Yeah. All right. Well, I will leave it there for this week. If you have difficulties, feel free to message me or Rebecca between now and next week. Aman, you had a question?
It's sort of related, sort of not. I came across this package called Number, and it seems promising. Have you used it ever?
I have tested Number. So the idea with Number is that it's supposed to be a replacement for NumPy, with the idea that as you write, as the code gets executed, it kind of in the background quickly recompiles it as C code and then executes it for you in that way. And I think it also has the option of using GPU resources if they're available. It sounds really good to me, and I wish I could say that I had used it to great success. My problem has been twofold. One, I started testing NumPy Number ages ago, back when it had only a very small fraction of the NumPy library covered. So it was missing a lot of the functionality that I wanted. Also, I've never been able to get my GPU libraries properly installed on my desktop at work, and so I could never use the GPU. I acknowledge that both of those situations will have changed in the, whatever it is, 5 or more years since I looked at that package. And so long as it's being developed, I think it has great promise. I'm hoping very soon I can get a new operating system, or ideally a new desktop machine for work, so that I can actually start using GPU resources. So yeah, maybe in a few months I'll have a different opinion.
Cool, thanks.
Okay. All right then. As I was saying, have a go with some of the optimization work. If you get lost or it gets too hard, don't stress, because this is meant to be me teaching you how to do some optimization. So we're going to go through it at the start of next week, but I just find it helps if people have thought about it and had a little try for them first, try for themselves first, because that often generates a lot of useful discussion. So I think I will leave it there, and we can pick this up again next week.
Thank you, Paul.
Thank you.
Yeah, thanks.
All right. See you, everybody.